So in this video we're going to look at section 13.3 again, but we're going to focus on the geometric interpretation. Interpretation of the partial derivatives f sub x and f sub y. So this is the previous video. In the previous video, we just focused on computation. There were two ways that we could compute the partial derivative f sub x. You had two ways. You could do the derivative with respect to x of the function, and what I'm assuming here is that f, you're given, let's state that at the beginning, z is equal to f of xy. This is a given. So you're going to focus on the computation of these partial derivatives, and you're going to take the derivative with respect to x of x hold y constant. And you're going to do that, and that is the meaning of the partial derivative of f with respect to x. There is a limit definition. This has a limit definition, but I'm going to omit that and just focus on our Calculus 1 skills, and I would prefer to focus on the geometric interpretation. There's a partial derivative of f with respect to y, f partial y, that would be the derivative with respect to y of f hold x constant, and y is your variable that can change. And again, this also has a limit definition. Together we call these, the way to compute the partial derivatives, we called this method 1. And then there was a second method, method 2, for partial derivative of f with respect to x, or the partial of f with respect to x. To do this more in terms of parametric formulation, derivative with respect to t, f of x plus t comma y, and f sub y to be the partial of f with respect to y, the derivative with respect to t, derivative with respect to t of f of x comma y plus t. Okay. The subject of this video is that my claim is that method 2 has geometric implications, and that's the subject of this video. Okay, so if you want to see the actually examples of computing partial derivatives, you should watch the previous video. This video is going to be on the geometric interpretation of these partial derivatives. Okay, so the skills that you're going to need. The skills needed. We need to remember the curves on surfaces. Curve on surface. Okay. And we know that if you have what's called a c of t, it's a vector valued function in one variable. You pick your favorite x of t, your favorite y of t, and then you have your function f of x and t, y of t. Okay. And there is your curve on your surface. So this is the picture, and we won't need anything quite this complicated, but you pick some crazy curve down here. Here is your x of t, comma y of t. Okay. The crazy thing on the surface, that's your x of t, y of t, f of x of t, and y of t. Okay, and this was your given surface z is equal to f of x and y. Okay, so the nice thing about this section is we don't need anything quite nearly so complicated. The only curve that you need down here in the xy plane, the only curve you need in the xy plane is you just need to remember also just your lines. Let's take L of t. Okay. And remember this, if you pick x naught plus t, y naught, okay. This is an example of a curve, okay, in the xy plane that goes through the point x0, y0, and it picks some different values of time, and it would be a curve that's a straight line that's moving in the x direction. So at this point, you would have a direction vector. The direction vector of this line is going to be 1, 0. Because you can do the algebra here, that this would be x0, y0 plus 1 comma 0 times t. It's just an equivalent way to write it. Okay. There's another curve you could write down, L of t, to be x0 comma y0 plus t. Okay. And that would be equivalently written as x0, y0 plus 0, 1 times t. And that would be a curve that goes through, it's in 2D, goes through some point x0, y0 that you're interested in, and is going in the y direction. There is your vector v, 0, 1. So there's your direction vector, and here is your point. So this is of the form p plus v times t. It just so happens to be in 2D. So then you know that if you have maybe some z is equal to f of x and y, this is just kind of review at the moment, you should be able to then make a curve c of t, okay, to be x0, say y0 plus t, f of x0, comma y0 plus t. Okay. Observe a couple things at this point. If you choose t is equal to 0, that means your curve evaluated at t is equal to 0, then you'll get the point x0, y0, f of x0, y0, which is just a point, and this is your z variable, right? It's not just any z variable, it's the z variable that's on that surface. So this curve c of t, if you had to describe it just in general terms, okay, it's in 3D, so we got to think about that. This part of the curve, well, that's what we had before. That was a little L of t. Here is x, here is y. Here is some point x0, y0. Okay. C of t has 3 variables, 3 entries, but the first 2 tell me that I'm looking at kind of a curve here in the y direction. Okay, this is like your L of t. And then you had some sort of surface, right? Z is equal to f of x and y. And that's maybe the curve. Here's your curve c of t, pasted onto the surface. That's your curve c of t. Okay. And at t is equal to 0, you're right over top of the point x0, y0. You are at the point x0, y0, the function evaluated at x0, y0. Okay. So there's your general picture. This is, I hope you can see why I'm maybe referring to this, because if you look back here at your partial derivative method 2, you can see I'm taking time derivatives and I'm putting into my function some x plus t, y. This is the equivalent, maybe down here, of choosing a curve in the x direction, not just any curve down there, but just a straight line. Okay? And then you're going to paste that onto the surface. When you do this other partial derivative, you're going to let x be some number, or leave it alone, and then be y plus t, in which case you'd be looking at a curve going in this direction. So nothing really crazy, no crazy curves down here, just straight lines. Paste that curve onto the surface, okay? And now you have these kind of lines that intersect here at the point, x comma y, f of x and y. And my claim is that the partial derivative has something to do with these curves, and that's what we need to discuss now. So let me start an example and just do kind of motivational example. let's say that your function, f of x and y, let's not pick too crazy a function here, is x and y, x squared times y. Okay. Now we know from the first video that f sub x is 2xy, and we know that f sub y is equal to x squared. Okay. And you could get this via whatever method you prefer to use, whatever method. Method 1 or method 2. I think just for getting the answers, method 1 is easiest just to get answers. Okay. Method 2 will tell us like what's actually going on. So let's take a look here. Like, what if you picked a point of interest? If you pick a point of interest, let's say that you pick your point x naught, y naught to be 1, 2. Okay. Now notice, you can just take this x naught, y naught and plug it into your function, f of x naught, y naught. And that's a no-brainer. You should get 4. Okay. Once you get that value, you can then put them all together into a vector. You can say you have x naught, y naught, f of x naught, y naught. Okay. And then you would have the vector 1, or point in space. This would be a point on your surface. Okay. So if we're sketching a picture of all that we've done so far, I just have some sort of surface. Okay. I had the function f of xy was x squared times y. We picked a particular point down here, 1, 2. That was our x naught, y naught. Okay. All I did is I've evaluated my function at that point. So we have 1, 2, 4. This is our point x naught, y naught, z naught. Okay. Now observe the following. Just like you can evaluate the function at x naught, y naught, you can also evaluate your partial derivative at x naught, y naught. And you've computed them via whatever your method is. This is what you're going to get. So observe that if you have the function f of x naught, y naught, f sub x evaluated at x naught, y naught, that would be 2xy evaluated at x is equal to 1 and y is equal to 2. And what should that give you? That should give you 4. Okay. And f sub y evaluated at x naught, y naught, that should give you x squared evaluated at x is equal to 1 and y is equal to 2, and that should just give you 1. Okay. So we have then computed these partial derivatives. Right here we've got 2 partial derivatives. Partial derivatives at the point x naught, y naught. I mean, the question is, meaning, what are these numbers? What did we just do? Okay. So my claim is the following. I will draw it on the picture and then we will back it up with a computation. My claim is that we're going to look at 2 curves, one going this way and one going this way, through that point 1, 2. Here's your x-axis, here's your y-axis. So this is the curve right here through the point x naught, y naught in the x direction. This curve here is the curve in the y direction that goes through the point x naught, y naught. You're going to paste those curves onto the surface. Okay, like this. You're then going to compute tangent lines to those 2 curves. Okay? And then you're going to look at the direction vector for the tangent lines. And my claim is that these partial derivatives are the z entries for the direction vector for your tangent line to these curves. Okay? So let me summarize that real quick. Just a summary of what I just said. Okay. 1, you're going to create lines in the x and y direction in 2D, meaning down here in the plane. You're then going to project lines onto the surface. Now clearly that's happening in 3D because our surface, so we're talking about getting these curvy lines on the surface. That's step 2. The first step was to kind of create these lines through the point x naught, y naught. You're then going to, step 2, create these curved lines that go through the point x naught, y naught, f of x naught, y naught. The third thing you're going to do is you're going to compute tangent lines to each of those curves. So you're going to then have your surface, you're going to have those curves in the different directions at this point. You're then going to compute these tangent lines. Okay? And because they're lines, I mean, they're nothing more than lines, so they have to be of the form p plus v times t. So you know the point that they're going to go through. The point is going to be x naught, y naught, comma, z naught. Sorry. F of x naught, y naught. That's the point that they go through. And then the vector, my claim is that the vector is going to have 3 entries because it's a vector in R3. And my claim is that the numbers that you've computed with partial derivatives, partial derivative numbers go here. Okay. So that's a summary of what we're going to do. Okay. Let me do one quick computation for you. Okay. Let me give you show you how method 2 has something to do with computing these partial derivatives. So we showed via method 1 that f sub x evaluated x naught, y naught was 4. Okay. So let me show that via method 2 real quick, and then show how it matches what we've done in these 3 steps. So first, you're going to look at the function f of xy is a given. It's going to be x squared y. I think that's the function we chose, x squared y. Yup. Okay. And we chose the point x naught, y naught was 1, 2. Okay. So remember, f sub x is going to be the derivative with respect to t, the function evaluated at x naught plus t, comma y naught, and then evaluated at t equals 0. Okay. And if you follow through with that, you should get 4. Oh, is it 2, 1 or 1, 2? Give me a second. X is equal to 1, y is equal to 2. Okay. So if you do that, derivative with respect to t, 1 plus t squared times y naught is 2, and then you're going to take a derivative and evaluate at t equal to 0. So that should give you 2 times 1 plus t times 2. That's otherwise known as 4 times 1 plus t. Then evaluate at t equals 0, and you get 4. Okay. So what did we just do here? My claim is that this computation contains in it the steps 1 through 3. So what did we do? You looked at a line, L of t, through the point x naught plus t, comma y naught. This was the equivalent, right, of 1 plus t, comma 2. This was the equivalent of, here's your point x naught, y naught, 1, 2. You then computed a line in the x direction. There is that line, L of t. Okay. You then put that line onto the surface. You made a curve. Okay. You made a curve. That was the curve 1 plus t, comma 2, comma 1 plus t squared times 2. There's your curve on your surface. You then can take a derivative with respect to t. That would be x prime of t, y prime of t, z prime of t. That z prime of t is what we've got here, the derivative of the function. Okay. This right here is the derivative with respect to t of this function evaluated at 1 plus t comma 2 evaluated at t equals 0. So just do the c prime of t. So let's finish c prime of t. That would give you a 1 comma 2 comma 2 times 1 plus t times 2. Okay, that gives you 1 comma 2 comma 4 times 1 plus t. Okay, look familiar? That's what we got back here. Then you evaluate it, c prime of 0. That's 1 comma 2 comma 4. Okay. My claim is that, again, this number right here, that was your partial derivative of f with respect to x, evaluated at x naught, y naught, which was 1, 2. Okay. So what we just did here, we made our curve on our surface. We had the curve line through the point x naught, y naught. We then made a curve on our surface that went in that direction x. We drew it. There's our curve c of t. We then found c prime of 0. C prime of 0 is nothing more than the direction vector for the tangent line to c of t. That's what c prime of 0 is. You need the t equal to 0 so that you can be looking at the point x naught, y naught, f of x naught, y naught. That is your point c of 0. Okay. So that's the significance of the 4. So let me bring in a video, or let me bring in a Mathematica document so you can kind of see all the things that are going on here, these computations. Okay? And by computations, I mean showing that you can see how this tangent line to the curve c of t, okay, which in this case is 1 plus t comma 2 comma 1 plus t squared times 2, that the tangent line to this curve at t is equal to 0, which is otherwise known as the point p is equal to 1 comma 2 comma 2. So at this point, we've got a tangent line. The way you compute that, it is an L of t. It goes through the point 1, 2, comma 2. The direction vector is c prime of 0 times t. C prime of 0, we decided was 1, comma 2, comma 4 times t. Oh, c prime of 0. Hold on a second. Oh, the derivative here is 1. This should be a 0. The derivative of 2 is 0. You've got a 0 here and a 0 here. Sorry about that. This should be a 0. Okay. So what I'm seeing is that this is the point that our tangent line goes through. This is the vector times t. So here we can see our direction vector, that it's pointing in the x direction because we have a 1, 0 here. This number 4, that is what you're using your partial derivative at 1, comma 2 to give you. Okay, so it's the third entry of the tangent line